Hi everybody, I'm Peter Diamandis. Welcome to our course on our quantum future, how quantum tech will impact our world. And I'm here with my dear friend Jack Hidary, who is the expert in this field, is going to be teaching this course, and I'm here to be your eyes and ears and ask the questions that you might want to ask of him. So let me introduce Jack. So Jack is a successful serial entrepreneur. He established his first company, Earthweb Dice, as a company that he ultimately took public. He then led his company through 12 quarters as a public company, which is extraordinary. The company is now on the New York Stock Exchange. Jack currently leads AI and the quantum group at Alphabet X, formerly known as Google X. Jack focuses on both the foundations of AI and the applications of AI in the real world. So he's also the co-author of numerous publications on AI and quantum computing. He is the author of this new book, amazingly, Quantum Computing: An Applied Approach. We'll talk about what's in this in a little bit. So Jack, let's jump in.
It's great to be here, Peter.
It's great to have you here, pal. You've outlined 4 modules that we're going to go through, individual parts. The first on the introduction of quantum and the quantum basics, which is probably the level that I remember from my quantum courses back at MIT. And then quantum sensing and quantum communications, and then we'll dive into what you defined as part 1 and part 2 of computing sciences. So let me turn it over to you, and let's jump in.
Sure.
So
Peter, I think, to start off, why don't we go back and let's recap quantum mechanics itself, because I think that the 3 modules that we're going to go through, quantum sensing, quantum communications, and quantum computing, are going to make a whole lot more sense to us and everyone viewing this as we go through understanding these core fundamentals. And these are really surprising kinds of things about our world. If you recall back from your college days, what's interesting is that in the year 1900, Max Planck and Albert Einstein and all the scientists of the time were faced with the reality of crisis. There were things they were seeing in their measurements that did not make sense with the classical theory they had from Isaac Newton. The theory that held us going for 200, 250 years just wasn't jiving with experiment. And so it forced a crisis. Yeah, that's a crisis. And so it forced a new theory to be born. Max Planck started that revolution in a talk that he gave, in a paper that he wrote up about that in the year 1900. Albert Einstein followed through in 1905, his Annus Mirabilis, his miracle year. We had 4 blockbuster papers. We should all aspire to have one of those papers.
How old was he then, you think?
He was about 29, about 30 years old at the time, and he had this Annus Mirabilis. And in fact, he got the Nobel Prize, his Nobel Prize, not for the special theory of relativity, not for the general theory of relativity, not for anything in relativity, which is what often he's associated with, but actually his 1905 paper that helped establish the foundations of quantum mechanics itself. The paper on the photoelectric effect. Yes. One of the crises that physicists had at the time was, how is it that we have photons coming down from the sun or from a light source, impinging on a piece of metal and getting one of those electrons to bounce out of its place? The photoelectric effect that is the basis of solar panels today and so many other types of phenomenon. This was a big conundrum and puzzlement. And sure enough, Einstein, building on what Max Planck did in 1900, explained it using what now we call quantum mechanics.
Amazing.
And so let's now go through and talk about some of these core concepts. So the whole world of computing that you and I are familiar with, that we grew up in, we were born in.
We call it classical computing.
Classical computing. So anything that's not quantum, let's just call it classical, right? And so we're in the upper left-hand quadrant today. That's been since 1950, the earliest real digital computers till today. We're in the upper left-hand quadrant of this chart right here. Classical data, what I mean by classical sensors is stuff coming from EKGs, from brain scans, from all kinds of different sensors that we can get, and then we process it on an Intel chip, an AMD chip, a chip that's in our phones, on our laptops, and our big cloud servers, on our supercomputers. All these are classical processors.
We'll take an analog signal and turn it to ones and zeros.
Right, it'll take any kind of signal, analog, digital, make sure it's ones and zeros, and then process it in what we know today as programming languages on a processor with a CPU and memory and hard drives and all the stuff that we know today. And that is the realm that we've all lived in for the past 70 years. But we're now about to enter the lower right-hand quadrant, this QQ quadrant, a quadrant where 2 new innovations are coming together. new kinds of sensors, these quantum sensors, we'll be talking about that in a minute, and then, most importantly, the ability to process information on a quantum mechanical computing device. A device that was conceived of years ago, and we'll talk about the birth of this idea. And now you and I, Peter, are living in the moment where in the last few years, labs and companies around the world have actually built these devices.
It really is this moment.
This is it.
It was just recently a team at Google announced quantum supremacy, which is extraordinary.
It
and
is.
You'll describe what that means.
We'll describe exactly what that means. This is a Sputnik moment.
Yeah.
This is a Sputnik moment in the computing world.
Nice.
And it's really exciting to be living and to be with so many exciting other researchers and companies in the space. So that really precipitated my writing this book, because were there books about quantum computing? Sure, there are a number of great books about quantum computing, but Peter, these were written 10, 15, 20 years ago, before this very moment where we actually have these incipient devices that we can actually program and run. And so there was a need for an updated book that actually took all the theory and understanding from the past 20, 30 years and built on that to offer people the ability to actually program, code, and understand the applications of this kind of computer. So let's look at this. Before we get into all the science and the details, how are people going to use this, and are people going to use this? Well, the World Economic Forum, the folks who create the Davos conference every year, they went out to the CIOs, CTOs of the Global 1000 companies and interviewed them and surveyed them and said, hey, over the next 3 years, between 2019 and 2022, how likely are you to adopt this series of technologies? And they were asking about cloud computing and mobile and IoT and the usual things that we talk about. But sure enough, in that list is quantum computing. And to my surprise, quantum computing came out at 36%. Now, if you had asked me intuitively, I would probably have guessed that CTOs, CIOs might have said maybe 5% of them or 10% of them might say they're going to adopt quantum computing. But the word is getting out. Articles are being written in the business press, certainly, and I think soon maybe the popular press. And books are coming out, more materials are coming out. So CTOs and CIOs are beginning to see that this has enterprise applications. And today, in the course of our segments today, Peter, we'll talk about what those applications are for these large trillion-dollar industries. So today, Peter, we're going to go through 3 core pillars of the quantum information sciences area. So QIS, quantum information sciences, that's our big topic today. We're going to drill into computing, sensing, and communication. We'll spend most of the time on computing, but before we do that, we'll kind of take a quick tour of the land of sensing and the land of communications before we get to our final destination in computing.
I love it, love it.
Cool. So as we kind of tour this general space, we can see from this particular chart here, and first really focus on the horizontal axis on the bottom. And
what does that say?
That's the number of qubits that you can actually address and control in a system. So 1 qubit, 10 qubits, 100 qubits, maybe up to 1 million or 10 million qubits. And what you can see from this chart, which is so interesting, is that while quantum computing in 2 blue clouds that you see there, let's talk about the left blue cloud. Yes, we're in that regime right now. We're in that period right now where we can control 50 to 100 qubits individually and address them and manipulate them and read them off, after that. So that's the first blue cloud on the left. We're in that space right now. But notice that quantum communication and quantum sensing need far fewer qubits. They need between 1 and maybe 20 qubits. We certainly can do that today. So while quantum computing gets a lot of the headlines out there, actually, I'd like today for you and I to put a bit of spotlight on these 2 other pillars of quantum, sensing and communication, because actually they're even more near term.
Amazing.
Okay, so before we dive in, we talked about Albert Einstein a little bit and how he was there, literally one of the founders of quantum mechanics itself. The whole idea that the world is not necessarily continuous in all its phenomenon, but maybe discretized, and thus the word quantum from Latin, quantum, how much, right? And so how much, i.e. a unit, a specific unit. So it turns out that electrons running around a nucleus of an atom cannot be anywhere in distance from that nucleus, but they have to be in discrete orbitals or levels of energy away from that nucleus. So that's an example of a quantum phenomenon. It's not continuous, it is discretized in units of energy levels, we say, from the nucleus itself. So that's an example of something that is discrete, not continuous. And Albert Einstein had a big hand to play in 1905 and subsequently in forming what we know today as quantum mechanics. Yet, here he is, towards the end of his life now. This is only 3-4 years before he died. He was inquired with a letter from one Daniel Lifkin from New Jersey and asked him a couple of interesting questions about quantum mechanics. Daniel's son Seth brought this letter to me. This is a personal letter from Einstein to Seth's father. And in it, what does Einstein say? He answers the question about quantum mechanics and then goes on to say this, and I highlight this from the letter that you just saw, that this theory of quantum mechanics reminds Einstein of a system of delusionary thought from a paranoiac, okay, concocted in incoherent elements. And so what does that mean? That means that even Einstein himself, Peter, could not really embrace ultimately the implications and the weirdness of quantum mechanics.
And it must have been so extraordinary because as scientists, they were used to very, very clearly defined rules,
observations,
laws, and here comes something that makes no sense.
Right. Intuitively, it doesn't make sense, yet it is the most tested theory we've ever had in science. It has been tested and retested, and it makes predictions, and those predictions are right, and so we know this is true. Now, just because our human minds are not really capable of wrapping ourselves fully around it doesn't mean it's not true. And you, in your courses, constantly are talking about how exponential thinking, for example, is very hard for the human mind to wrap itself around. The old adage of the person who came to the king and did a wonderful thing, and the king said, take anything you need. And he said, I'll take 1 rice on the first square of my chessboard, 64 square chessboard. I'll take double that, 2 grains of rice on the second square of this chessboard, and then we'll double from there. And sure enough, the king said, oh, of course you can have that. I mean, what's a few grains of rice in my kingdom? But of course, we now know that this was more rice than ever was produced, in the history of humans. And so the fact is that exponential thinking is very hard for humans to think of. And in an analogous way, the quantum way of looking at the universe is also difficult. Now, one of the things I think we may want to do, and this is the subject of another video, Peter, one day, would be to actually do what happened to me. Due to unusual circumstances, I actually learned quantum mechanics before I learned Newtonian mechanics.
Wow.
And so for me, quantum is my intellectual home. It's where I grew up in. And it's how I see the universe. Later, I learned about Newtonian mechanics and the details thereof. And I said, okay, I can see that, but let me go back to quantum because that's how. So part of it is also education. Just like we're doing here, we're doing an educational seminar here today, and you do so many educational seminars on exponential thinking, which helps people break out of linear thinking. So too, I think we need a revolution in the educational system that allows us to teach quantum first, and then this. And how do I know that might be the case? Because I've taken my own nieces and nephews as guinea pigs. And with all 8 of them, I've trained them in quantum before they got to know physics.
What age was this?
They're kids now. They're between 7 and 17 right now. And so this is a real-time experiment. We'll see how
I love it.
We'll come back and we'll give you an update. But the fact is that this is something that I think we may want to talk about in education. So let's now go to the core principles of quantum mechanics so we can set the stage for the rest of our talks today.
Perfect.
Does that make sense?
Yeah, let's do that.
Superposition. This is the first interesting aspect of quantum mechanics. In the classical world, we have what we call constancy, and we also have the fact that measurement doesn't affect the object itself. If we can use maybe the book, perhaps, as a prop over here. And so we have this book, and if you and I touch the book, weigh the book, look at the book, impinge light on the book, have it bounce off to our eyes.
It's consistent. It's
consistent, and it does not change the book itself, right? And so we do measurements on things in the classical world. Again, by classical, we just mean non-quantum, right? The pre-quantum world. And it does not change the object itself. And also, if I put it behind me and we don't observe it for some period of time, we assume it's still behind there, right? And so those are things that we're used to, that our intuition tells us about the classical world. Not so in the understanding that we have from quantum mechanics. In quantum mechanics, we now understand that when something is, say, for example, at the subatomic level, it is not necessarily just in this one state, and when you measure it, nothing happens to it. In fact, measurement profoundly affects the state of that object. And we'll see why that's so important in all the things that we'll talk about today. And so how do we find this out? Well, in 1801, 100 years before even quantum mechanics, Thomas Young did an experiment called the double slit experiment. And everyone maybe has heard.
It was that long ago?
It was 1801,
wow.
Yet he couldn't make sense of it. What did he find? At that time, and for the next 100 years after that, there was a big controversy. Are phenomena that we see in nature particles or waves?
Right.
Is a photon, which was not named until 1920, but say a piece of light, let's call it that.
A unit of light.
Was it a wave or was it a particle? Was an electron a wave or a particle, right? This was really unknown, and there was a lot of going back and forth. Without going into a lot of details, here's what the double slit says. If I have an electron beam gun that shoots out electrons, and I just shot them through one slit, say in this two-slit experiment, and it then hit a screen that is detecting those electrons on the other end, what do I expect to happen? Well, if it went through the left slit, it would appear on the screen right behind the left slit. If it went through the right slit, it would appear on the right slit. And so
that's what
classically, this is what our expectation would be.
Like the bullets going through.
Bullets going through, a certain slit as well. And so what we'd expect it to appear if we're going to have a randomly shooting gun that goes left, right, left, some kind of combination, we'd expect to see a huge number of dots for the left and a huge number of dots on the right and nothing else. But Peter, that's not what we see. What Thomas Young saw and what people repeated again and again, and I just recently built an interferometer to again show this, just to show it to various colleagues,
your nieces and nephews,
is that we see a pattern of interference. What does interference mean? It means that what we see is not just two bright lines. We see that there are multiple lines of varying degrees of strength of how many electrons hit. And in fact, we see areas of complete dead zones where there was interference and there's no pattern of electrons there at all. What does that mean? That is the hallmark of a wave, not a particle. That is something where if I had two waves, we can put this back now, if I had two waves that are in a wave pool and they were coming towards each other, we know that if one of the peaks of one wave hit the peak of another wave, they would even go higher. Constructive interference. If one peak hit the trough of another, destructive interference, we get nothing, as we see over here. And then, of course, trough, we get even a deeper depression there. But let's just take these two cases of the peak and the trough, and that would explain the dead zones between these bands. And the intense areas would be explained by peak, right, coming, and trough coming. So that actually would explain very well.
So this is evidence for electrons, in this case, as a wave.
As a wave, and more specifically, that we now have repeated this experiment over the past 100+ years with just one electron going through at a time. And we still get this pattern. What does that mean? That means that the electron itself was in a superposition. That is, it was in a combination of states of left and right slit, right slit, before it finally reached the screen when it was, quote, measured.
Right.
And then it hit one of those areas. So in fact, something can be not just in one state or another, it can be in some combination of these states. More specifically, more accurately, what we say in physics is, it's in an indeterminate state of superposition.
Until it's measured.
Until it's measured. And so often in the popular press, Peter, you might read that something is in this and that, but actually it's more accurate for us to say that it's an indeterminate state of superposition. Then we measure it, and it, quote, collapses to one state or another. Now, for another time and another day, we'll talk about the philosophical implications of how does our universe collapse things, and what does that mean? And there's a whole body of interesting literature on that.
And are we living in an infinite number of universes?
Exactly. Yes, and Hugh Everett had something to say about that in 1957 in his thesis, and that is where we get the many worlds hypothesis of Everett. But we'll leave that to another day, and now we'll go on to the next slide, where we'll talk about Schrodinger's cat and how that exemplifies the idea of superposition. So a lot of people have heard about Schrodinger's cat, and why did Schrodinger do this, and what does it mean? He wanted to show that even something in the subatomic world could have implications at the larger macro world that you and I exist in. And so what we have here is a cat in a box. The cat hopefully is initially alive, and in our parlance today, it's a little too harsh to say dead and alive. So I just say asleep and awake. Okay, let's do that. Okay, so initially the cat is awake, And there's some kind of potion in that vial that you see there that will put the cat to sleep. Okay? And just take a little nap for a while, right?
Kinder, gentler Schrodinger.
Kinder, gentler Schrodinger, right? Okay. He was a little harsh in the 1920s and 30s. So we have a radioactive substance there, say uranium or some kind of radioactive nuclide, and it's going to emit on some basis that is quantum, right? Because radionuclides, as they decay, that is a quantum phenomenon. We can't predict it. We don't know what's going to happen. And it's going to hit that lever, and if it does hit that lever, it's going to smack that potion, and the cat will take a nap for a few hours, and of course come back alive after that. So the fact is, if we close this box up and we can't observe it ourselves, what happens to the cat? And this is the idea of Schrodinger's cat, that when we close that box and we don't know whether the radionuclide, that uranium, has decayed or not decayed, has emitted or not emitted its radioactive emission to cause this to happen, the cat is in a superposition of awake and asleep. So this was Schrodinger. So when people hear about Schrodinger's cat, I just want folks to relate it to this idea of superposition. Now let's go to and kind of foreshadow something we're going to talk about later in computing, which is this idea of the quantum bit, the qubit. Okay, so you and I very much know about bits. Bits, short for binary digits, could be a 1 or a 0, a 1 or a 0. And that's a well understood idea. If you and I are typing in a word processor, we hit save, where do those words go? We take the word Peter Diamandis, those words, and we translate it to 1s and 0s, and they get stored in transistors and memory in the actual computer in a series of binary digits, 1s and 0 bits, binary digits, bits, 1s and 0s. So that's great, but in the quantum world, we have more possibilities. We have the ability of having a quantum bit or a qubit. And here, we can have the possibility of some kind of system, we'll talk about them in a little bit, which can not only be a 0 or 1, it can also be in a superposition of 0 and 1. Just like the cat can be in a superposition of awake and asleep. This new kind of bit, this qubit, can be in a superposition of some amount of 0 and some amount of 1. And therefore, we have a much wider computational canvas, because now the actual unit of computation itself, the qubit, is a much richer world than just 1 or 0. And we're going to come back to this idea, but let's now relate to entanglement. So one special case of superposition, Peter, is the idea that two things can be entangled with each other. What does that mean? And this is one of the things that really irked Einstein, okay? Till the end of his days, he's like, I don't like this spooky action at a distance. And this spooky action at a distance...
Disobeying the speed of light.
Exactly. Well, it turns out it's not, but it turns out it's very, very spooky nonetheless, which is I can take two particles, I can bring them close to each other, I can perform a certain operation, and then I can intercorrelate them with each other in a certain special way, such that even if I pull them far apart, where you're on Earth and I'll go to Mars, or I'll stay on Earth and you go to Mars, and I have one of the particles and you have the other one, and I'll measure mine, and automatically yours is now already put in a certain state. So, and as an example, if we're correlated positively, that is, when I measure something as up, yours is going to be up. That will be one kind of correlation. In the graphic we have here, it's a reverse correlation, right? Inverse correlation, so that when I measure mine as up, you're going to measure yours immediately as down. Yours immediately is down. I know that for sure because we set it up in an entanglement that is inversely correlated. So think of entanglement as a special kind of quantum sense of correlation.
Sure.
That's how we're going to think about that. We're going to use that later on in our talks here today. So, Peter, that's kind of a summary of some of the core concepts of where do we get quantum mechanics to begin with, this crisis in around the year 1850 to 1900, a number of crises that came about, Max Planck, Albert Einstein, Dirac, Schrodinger, Heisenberg, Niels Bohr, all the key founders of the quantum mechanics field came together and developed this theory that we now know as quantum physics. And then, years later, as we're about to see, a number of theorists said, wait a second, I think we can use this for other kinds of applications, including quantum computing. And that's why superposition and entanglement, instead of just being theoretical things in a textbook, have now become the reality of a new kind of computer.
Fantastic. I hope you've enjoyed this module 1 on our quantum future. As you can see, Jack is a beautiful communicator and a brilliant man. And so if you stick with us into our next module, we're going to go into the whole realm of quantum sensing and quantum communications. Ultimately, now that we understand at least some of the basics, what can you do with it? How can you make use of it? So please join us for module 2. See you in a little bit.